my name is Lior Sinai, and today I'm going to be talking about why Julia is the best language for data science. So I'd heard about Julia from my brother, friends, and I'd read articles about it on the internet, but it was really this article, The Unreasonable Effectiveness of the Julia Programming Language, that really convinced me to learn Julia. This article spoke a lot about how scientists and academics who don't normally get excited about a programming language were getting excited about Julia. And they spoke about how it boosted the opportunities for collaboration and allowed them to use other people's code in unforeseen ways. And this was something I didn't fully appreciate when reading this article, but hopefully by the end of this talk you will fully understand how Julia makes integrating code so much easier. So what is Julia? In a nutshell, it is a high-level dynamic numerical programming language. And so its peers are other languages like MATLAB, R, and Python. It's not quite as general purpose as Python, but I think this is better because it's built much better for what it is supposed to do, and that is scientific program in numerical computing. So one of the first projects I implemented in Julia was a random forest classifier. So this isn't a talk on machine learning, so I'm not going to go into too much detail here. I think the important things are it's a relatively old algorithm. It was first introduced in 1995. It's fast to train and to use, and it also performs quite well on simple tasks. Hence, it's still staple machine learning, even with more advanced techniques like neural networks that are available today. So I had originally implemented this project before in Python following the Fast AI course by Jeremy Howard. So this here is a mock-up of the Python code, and it's written in typical object-oriented programming approach, which I'm sure most developers here are familiar with. So you have a class random forest classifier which has several attributes, and it owns methods which can only be called by instances of that class. So here's the Julia code, and writing it was a bit strange at first. Firstly, Julia is a functional orientated programming language, and so you don't really get classes. You do get structs, which are very watered down, lightweight versions of classes. And the methods exist in a global function space. Later on, I will be talking about multiple dispatch, which solves the issue of naming conflicts in this global function space. The other thing is that there are types in Julia, and they come after the variable name instead of before it, as is usual in other programming languages. Weirdness aside, one of the big wins is that my Julia code was much faster. So Python was still fast. It managed to fit 4,000 samples in 6.5 seconds. But the Julia code was more than 9 times faster and fitted the samples in less than 1 second. Of course, there are packages like scikit-learn in Python which have heavily optimized this problem and can fit it a whole order of magnitude faster. However, my point here is I got a nearly 10 times speed increase for writing the same code in Julia as opposed to Python. This gave me the confidence to try a much more complicated project. So this here is a transformer. Once again, not going to go into too much detail. It was first introduced in 2017 by Google, and since then it's taken over the field of natural language processing. It's a fairly complicated algorithm, but it works quite well. On the right, you can see my results for use case with Amazon reviews, where I was doing sentiment analysis. So I've labeled all the negative reviews with a 0 and all the positive reviews with a 1. And then what the model does is calculates a positivity score from 0 to 1, where 0 is very negative and 1 is very positive. And you can see for the most part that the 0 labeled reviews get a positivity score of 0, and the 1 labeled reviews get a positivity score of 1. There are some false positives, but for the most part, the algorithm performs quite well. So I'm going to demo this quickly. I'm going to be showing a lot of code. The point here is just to show what's possible with Julia. I will be doing simpler demos later on. Alright, so I'm going to run through this code quite quickly. It is at quite a high level. As I've said, the main purpose of this demo is just to give you a feel of Julia code and to show you what is possible in Julia. So the first thing I do is import registered packages, for example, the Flux deep learning package. I then import packages I've developed myself, namely the tokenizers light package and the transformers light package. I then define string processing functions, for example, to get rid of punctuation and Unicode symbols. I then load the pre-trained models. There are 3 models here. There's the tokenizer, which splits sentences into words, the indexer, which maps those words to numbers, and the actual model, which calculates a final positivity score based on those input numbers. This model has 251,000 parameters, which is really tiny for a transformer. The big commercial models have billions of parameters. So yeah, this is really small. I can then pass a piece of text. So once again, going to split that text into words and then map those words to numbers and then get a final score out. You can see I didn't quite know how to handle Stephen and Kings, but it did recognize the other words, and the final score of 0.82 is very positive. If I change a single word and rerun this, then you can see the final score is 0.005, which is very negative. So yes, this is a small model, but it does work quite well. Okay, so that was cool, but where would you need to use something like this in the business environment? And I think the big answer is data science. So data science is a relatively new term that's only been around for the last decade or so. According to Google Trends, it only really picked off in late 2014. So everyone has their opinions on data science, and maybe some of you are not too familiar with it, so I want to go into more detail about it and give my own opinions. I like to think of data analytics as a pyramid. At the bottom, we have the actual data, whether that be unstructured data like pictures, PDFs, Excel documents, or more structured data like SQL relational databases and NoSQL databases like MongoDB. There are all sorts of complexities with ingesting this data and storing it, but for the most part, we've got pretty good at this, even as data has grown exponentially. The next layer is securing and governing that data, and this includes both the software sides of things where you restrict access and apply encryption, and also the legal side of things, for example, the GDPR Act in Europe and the Protection of Personal Information Act here in South Africa. The next layer is cleaning and classifying that data and getting it into a useful form for people to use. Then, next we can analyze it, and this is plotting charts, key performance indicators, and doing basic statistics on it. As much as we developers might hate to admit, Excel is probably the most popular tool for this task. And right at the pinnacle, we have AI, artificial intelligence. So I want to say right out that I'm not talking about AI that can drive cars or talk to you like a human can. I'm talking more about algorithms that can get insights from data with very minimal human intervention, or algorithms that can reproduce a repetitive task. So an example of the former is the data clustering I'm showing here, where data is being split into 5 clusters based on 2 features. An example of a repetitive task that a neural network could do is text transcription for videos. So that is, of course, something that humans can, but there's no way they would be able to keep up with the demand as we generate millions of videos every day. Here is the whole pyramid, and we have several fields that cover it. Data engineering tends to work with the bottom two layers. Business intelligence goes over the middle three, and data science is the top two. It mostly focuses on the analyzing and the advanced algorithms. Although I have heard more than one data science moan about having to work across this entire pyramid. All right, so we've seen that data science sits at the intersection between three disciplines. There's the business side of things given by the domain expertise. There's the algorithms given by the mathematics and statistics, and the software where you actually implement those algorithms and process the data. For the rest of this talk, I'm going to be focusing on the software. So for data science, there are basically two main requirements of the software. The first is it has to be efficient for working with large amounts of data. And the second is it's got to be easy to share information and packages and algorithms. And the main reason is because there are so many of these algorithms and they can get very complicated, and you don't want to be implementing all of them yourself. And this has been a challenge posed to the data science community, and there's been a clear winner, and that is Python. There are many courses available today online, and I would also like to add in traditional universities, which wasn't offered when I was in university, and that wasn't too long ago. And most of these courses end up using data science for the actual processing and the projects and the assignments. This course here explicitly states that you're going to be using Python upfront, but not all of them do. So Python is an extremely popular language, and there are many tutorials available online for it, many books, and lots of forums like the question and answer forum, Stack Overflow, for debugging code. And this is one of the reasons why it's so popular. It's really a case of you should use it because everyone else is. Another advantage of having this large community is that there are many high quality packages available in Python. There's matplotlib for plotting, NumPy for dealing with maths, scikit-learn for machine learning, pandas for working with data, and the two big machine learning packages, PyTorch and TensorFlow, which are both backed by large corporations, Meta and Google respectively. So while everyone might have their opinions on what data scientists do, in practice, you just rarely end up importing these packages and using their pre-built algorithms. So why shouldn't you use Python? If it's so popular, what has everyone got wrong? Well, firstly, you're burning down the planet. No, seriously, Python is a very slow and memory inefficient language. So this here is a graph of various languages' performance on synthetic benchmarks, and it's been normalized so C speed equals 1. And this is on a log scale, so the 10 to the 0 line is C speed, and you can see for the most part, Julia approaches or even exceeds C speed. Whereas Python is up to an order of magnitude slower. We had already seen this with the random forest classifier where it was almost 10 times slower. The next problem with Python is it has many features which make programming it upfront easy, but can cause lots of problems for maintaining it and can introduce lots of bugs. So one of the things you learn when you're learning Python is duck typing. If it looks like a duck and quacks like a duck, it's a duck. And basically, there are no guarantees in Python that an object will behave like you think it will. There's no type checking, no interfaces, no inheritance. So instead, the strategy is give it a good name so that it tells programmers what it should do. Is this really the best approach for a programming language? Here's another example of a bug that's all too easy to introduce in Python. You can import a whole module like math, and that allows you to do things like take the square root of 2. However, you can easily overwrite the function or the module, and Python will do it with no complaints. The philosophy in Python is the programmer is always right. So we've now replaced math with the string hello world, and suddenly we can't take the square root of 2 because the string hello world has no attribute square root. Here's another feature of Python that can lead to bugs. It's very lenient with scope. So here, for example, I'm calling the function makeNumber, which then calls another function add2, which then requires access to the variable x. And in most programming languages, this will cause the compiler to fail because it won't have access to the variable x. However, here in Python, it's very easy to declare a global variable by mistake, and hence this code will work, and when we print z, the answer will be 5. And this is a real bug that I've had to deal with numerous times in Python. And basically, this leads to several problems and lots of frustration with integrating and maintaining Python code. And then this then leads itself to the two-language problem. So what is the two-language problem? Well, basically, all the big packages that are written in a program for Python actually know that Python is slow and memory efficient. They know that it can easily lead to buggy code. So they're not actually written in Python. Pandas, NumPy, and scikit-learn are written in Python, which is a superset of Python that allows you to additionally define static C types and also call the underlying C code more directly, which leads to much more efficient code. TensorFlow and PyTorch are written in an entirely different language, C++. In practice, this is what means when you want to find more about a function in your IDE, you'll only be able to see the function definition because the function body is written in an entirely separate language. So instead, I propose we use Julia. So Julia is a relatively young language. Development first started in 2009, and version 1 was only released in August 2018. Compare this to Python, which was first released back in 1991. However, since version 1 was released, we've had many releases of Julia, and we're actually now going on to version 1.8. And in my own experience, there have been massive improvements in that first 1.0 release. So you might be thinking, why create a new programming language when so many others already exist? And in their blog post, the founders justified this with, we are greedy, we want more. And they go on to say how they wanted all the best parts of these programming languages in one programming language. They wanted the speed of C, the dynamism of Ruby, the linear algebra of MATLAB, the string processing of Perl, the statistics of R, and the macros of Lisp, and they wanted it to be as easy as Python and as good as gluing programs together as the humble shell. Something that is dirt simple to learn, yet keeps the most serious hackers happy. We want it interactive, and we want it compiled. So this was quite a big ask, and you can see why development took so long. However, the language they've created is something incredible. Firstly, it's interactive, so you can write code in a console and get back answers immediately. At the same time, it's also compiled, and this means it's fast. Basically, the compiler can heavily optimize code for specific cases, which leads to much more efficient and faster code. Thirdly, the language has very clean syntax and it allows you to write very robust code. You just have to get used to the functional programming approach. This is really a case of come for the speed, stay for the syntax. While we're here, I also want to point out the macro, so that @functor dense, which is quite a cool feature. And there's also full Unicode support. So for example, you can use Greek characters like sigma in your code and it will work quite fine. This leads to code that's Julia all the way down. Well, almost. But in my experience, I found that packages are mostly written in only Julia, and I've never had to dig deep enough to go to the point where the underlying Julia code gives away to C code. There's a medium and growing community in Julia, and this means there are a few high quality packages available. Flux is the big machine learning package. Data frames is used for dealing with data and is your pandas equivalent, and plots.jl is used for plotting. There are also other packages which you won't find in Python. Images.jl provides a common interface for dealing with images and also provides image processing algorithms. This package relies a lot on types, and these don't really exist in Python, so there's no point to have an equivalent package in Python. The other package is differential equations, which is used a lot in academia, where Julia has an especially strong support base. And I've read that it's much better than the alternatives in other languages. Another big reason to use Julia is the multiple dispatch functionality. And what this basically is function overloading plus a typing system plus dynamic programming. It was originally introduced to deal with naming conflicts in the global function space. However, it turns out it can do so much more. I highly recommend watching this video, The Unreasonable Effectiveness of Multiple Dispatch, by one of the founders, to truly get an appreciation of how great it is. I will be doing a short demo of this shortly. But basically what's happening here is there are two packages, differential equations, which allows you to solve advanced differential equations, and measurements, which allows you to define variables with extra uncertainties attached to them. And now these two packages were written by completely different people, and there's no integration code. However, what Stephen was able to do over here is use both of these packages together, and they work seamlessly without having to write extra integration code. And on the right, you can see the outputs where it's plotting the results with the uncertainties, and he didn't have to write any additional code to get this to work. If that didn't make sense, hopefully this short demo will give a much better idea. So now I want to explain in detail what multiple dispatch is and show you how it works. So firstly, multiple dispatch is an extension of function overloading. And what function overloading is having one function but many different methods, which are all distinguished by having different arguments. So for example, we have the rand function, which is heavily overloaded with 81 methods, and this is quite common for Julia. And if we call the rand function with no arguments, it returns a random number between 0 and 1. If, however, we pass a type, then it returns a random instance of that type. A range is also a type, so we can pass a range and it will return a number within that range. Additionally, we could add an extra argument, an integer for the number of outputs we want. For example, 2. We can add further integers to specify the dimensions of the output. For example, if we want a matrix or even a multi-dimensional array. Lastly, we can define a pseudo-random function and set the seed so that our results are reproducible. So you can see however many times I run this, I always get the same answers. Okay, that is cool, but it doesn't really show you the power of multiple dispatch. For that, I'm going to use much more humble functions, namely the plus function and the multiplication function. So we're used to writing plus with this infix notation, 1 plus 2, but plus is of course a function and can be called like one. And as we can see in Julia, it's very heavily overloaded with 208 methods. Now the important thing is that when we call the plus function, it dispatches to a specific method that's been optimized based on the input arguments. So for example, with those two integers 1 and 2, it called this specific function defined in the int.jl file. If we work with floats, it actually calls a completely separate plus method, which is defined in floats.jl. If we combine these two types, an integer and a float, then we get a more generic method which first promotes the integer to a float and then calls that specialized float function above. We can also work with more complex types, for example, complex numbers. So you don't need to understand complex numbers. The main idea is that we have a real part, the 8 and the 5.1, that we add together to get 13.1, and an imaginary part where we add the 5 and the 6 to get 11, which is the imaginary component. And we can also add real numbers. And once again, there are different methods for these different types. Okay, so now we can have an idea and start to understand how that measurement package worked. So this is a very watered down version of what's actually in the measurements package. First, we just define measurements struct, which itself is a subtype of abstract float. And we can now create a measurement. For example, let's say we measure something that's 20 centimeters long, but we have a half a centimeter of uncertainty. Well, now we want to add 10 centimeters to our measurement. Unfortunately, this won't work because it doesn't know which method of plus to call. So we have to define it ourselves. Well, I knew that wasn't going to work. Julia has safeguards against modifying functions. So we have to use a different keyword, import, instead of using, to say that we want to import this function as well as modify it. Great, so we can now define our plus methods, and we can now add 10 centimeters to our measurement, and we can do it the other way around. All right, that's cool, but if we have an uncertainty with our first measurement, we should also have an uncertainty with the second measurement. Cool, so now we want to add these together. And once again, that won't work because we haven't defined a method for this. It's pretty simple to define a method. I'm not going to go into too much detail here, but basically we need to add the main values, and then we need to add the square root of the sum of the squares of the uncertainties. So this basically means that our uncertainty will always be bigger than any of the individual uncertainties, but it will be smaller than their plain sum. Alright, so that's pretty simple to write in Julia code. And now finally, we can add our two measurements together. And you can see our uncertainties by themselves were 0.5 and 1.5, but together they sort of cancel out, and our final uncertainty is about 1.58. All right, so I hope this slide now makes much more sense. The measurements package doesn't know anything about advanced differential equations, but it does define basic maths for dealing with measurement. It's the new measurement variable. Differential equations didn't know about measurements and uncertainties, but it does know how to break its equations into smaller math problems, and it can then call the appropriate methods in the measurements package. And hence, these two packages can work together without any additional integration code. If you do not, I really hope you find that as cool as I do. Alright, so this is a cool programming language. How popular is it? Well, not very. This is from the Stack Overflow survey of this year, and we can see that Python is one of the most popular languages. It's used by almost 48% of developers. Julia is on this list, but it's way down at the bottom, and it's 31 out of 42. The story is similar in South Africa. This is from the Offerzen State of the Developer Nation survey. Python is the most popular language in South Africa, whereas Julia is on this list, but once again, it's all the way at the bottom. It's 22 out of 26, just under other. So like other new technologies, we might agree it's cool, but it has some aspects that make it a bit goofy and less popular than you would expect. So I've been talking a lot about how Julia is a compiled language, and it's actually just in time compiled. So it will compile the code as you need it. And sometimes this can be really slow. I'll demo an example of that shortly. I'm first going to go through this exercise in Python. Python is a dynamic and interpreted language, so for these sort of things it's actually really fast. First, I've got to import NumPy for dealing with maths and a plotting package. Then I define my array. Then I square it, and then I can plot my parabola. Great, so that took quite quick. I'm now going to run through this exercise again in Julia. Firstly, Julia is a numerical programming language, so it natively supports working with maths, so we don't have to import any special maths package. However, we do have to import one for plotting, and this takes a little while because there's some pre-compilation in the background. However, this is much faster than it used to be, way back when version 1.0 was released. Next, we define our array, we then square it, and then we can plot it. Plotting takes about 10 seconds. It's quite a complicated function, and there's lots of pre-compilation that has to happen in the background. Alright, there it is. It didn't take so long, but as you can see, it wasn't instantaneous. Now I want to mention that if we run through this again, it will all happen instantaneously because it's already being compiled in the background, so the code is already ready and you can use it immediately. So normally in things like machine learning, where you have 100 iterations, it's normally a good trade-off to have one slow iteration up front and another 99 really fast iterations. However, for things like plotting, where the first iteration is really important, This is a very strong negative for the Julia programming language. Another problem with Julia is that you can't create standalone executables. Julia code always has to run in a Julia runtime, and this is quite a killer for production and for distributing your code. For example, you wouldn't really want to use this for a web server because it has to be running the Julia runtime and can't run by itself. The next problem is, at least in my experience, Julia is more complicated than Python. And I think this is really because it gives you more control than Python, and this means more complexity. I think Python really sets the bar low here, and I think it's worthwhile having a language that is slightly more difficult if it gives you so much other advantages like more robust code and code that's much faster. The other thing with Julia is that, sadly, the community isn't quite big enough. It's still missing lots of tutorials, learning material, packages, and just people and maintainers to actually write Julia code. However, it's not all doom and gloom. Julia downloads are increasing every year, although the growth last year was steady. There are more and more packages being released, making it easier to focus on the code you want to write instead of having to write another piece of code because someone else has already done it for you. Another big thing is that the yearly Julia Discourse views are increasing. So Julia Discourse is a question and answer forum much like Stack Overflow, except in my experience it provides much better answers for Julia. And the fact that more and more people are using it means more and more people are having problems with Julia code, which is a good thing, and they're finding answers to it on Julia Discourse. So Julia is very much a growing language. So if you got this far, I hope you're very excited about Julia, and you're probably wondering how you can get started with it. The documentation is always the best place to start, although we don't usually, but I highly recommend reading it, and it is quite well written. I first learned Julia on Julia Academy following the computational modeling course with applications to the COVID-19 pandemic. That course was made in early 2020, so it's a bit of a time capsule. However, it's still quite interesting to go through and in order to learn Julia code. As I just mentioned, there's Julia Discourse for asking questions and looking at answers, and I will say again, it's a much better resource for Julia than Stack Overflow. Earlier on in this year, there was JuliaCon, which is the big Julia conference, and there are lots of videos there that you can go and watch. I've linked to this introduction by Jose Storopoli. It's a 3-hour introduction to Julia, and I highly recommend watching it. Lastly, some shameless self-promotion. I have a blog post, liorsinai.github.io, where I write about various things, including some pretty complex examples in Julia, including that random forest classifier and transformer that I mentioned way back at the beginning of this presentation. So I'm not really one to believe in the AI singularity. However, I do believe that if robots take over the world, it's really going to be Julia that powers them behind the scenes. Thank you for listening.